continuation of direct proof, and this is particularly looking at using cases to prove direct statements. So to prove a statement is true, we sometimes need to consider different cases that the hypothesis could break into and prove that the statement is true in each of these cases. Let's look at an example. So suppose we want to prove the following proposition. If n is an integer and n squared divides n, then n is either -1 or 0 or 1. So to prove that's true, let's first do a little scratch work on the side because the angle isn't necessarily obvious. So on the side we could look at some scratch work and just think about, okay, what does it mean for n squared to divide n? That would mean that n is equal to n squared times c for some integer c. And then we're trying to prove something about n. So we want to get n isolated. So if we wanted to get n by itself or relate it to c, what we could do is say divide both sides by n. And we could divide both sides by n squared. If we did that, then our equation would become 1 over n is equal to c. Okay, that seems useful. Is there any reason we couldn't divide by n squared? Well, we know that we can't divide by 0. So we're actually going to have to treat this as two cases, and our two cases will be n not being 0 and n being 0. While we're over here on the scratch paper side, we might as well think through the whole proof and see what's going to happen. So when n is not 0, when we can divide both sides by n squared, well, n not being 0 means n squared is also not 0, and so we can divide both sides by n squared, obtaining the equation 1 over n is equal to c. All right, what values can n have in that case? In that case, c is an integer. C is an integer, and n is an integer as well. And since c is an integer, this means that n could only be 1 or -1, because those are the only values of n that allow 1 over n to be an integer. If n is equal to 0, then, okay, we're trying to figure out, is it true that n squared divides n? Well, if n is 0, then 0 is equal to n squared times 0. So yes, this is true in that case as well. So if n squared divides n, then n could be 0, or n could be 1, or n could be -1, and those are our only possibilities. So now that we've sort of worked through that, let's write that out formally as a proof. So proof, we first start by assuming that the hypothesis is true. We assume that n is an integer and n squared divides n. That will be true in each case. Now we can break this down into cases, and our cases are n is equal to 0 and n is not equal to 0. So case 1 is n is not equal to 0. Doesn't matter what order you approach these in. So now since since n squared divides n, we know that means that n is equal to n squared times c for some integer c by definition. All right. Now we know that n is not equal to 0. So since n is not equal to 0, n squared is also not equal to 0, and we can divide n equals n squared c by n squared to obtain 1 over n is equal to c. Since c is an integer, 1 over n must be an integer. So n could only be equal to 1 or negative 1. Okay, so we have completed case 1 and followed it all the way through and found that if n is not equal to 0, then n must be 1 or negative 1. Our other case, if n is not equal to 0, then n is equal to 0. And in this case, we can observe that 0 is equal to 0 squared times any integer k. And so by definition, 0 squared does divide 0. Now we've examined both cases and seen that it will either become true that n is 1 or negative 1, or it will be true that n is equal to 0. So therefore, the original statement is true. If n squared divides n for an integer n, then n is in the set negative 1, 0, 1. Okay, so let's do another proof that requires cases. We want to prove the following proposition. If n is an integer, then n squared plus n is even. So I'd like you to pause and think about this. Some questions are, what are the cases? So what are the necessary cases? And another question is, how to get started. If you can, try to prove the whole thing. And if you get stuck, then you can take a look below. So pause and start to think about the proof for this one, and we'll talk about it in just a moment. Okay, so let's talk about this proof. So let's do some scratch work over on the side to start off. We want to show that n squared plus n is even. If we want to show that n squared plus n is even, by definition, we want to show that n squared plus n is equal to 2 times t for some integer t. So for some t in the integers. That's our goal. In the beginning of this chapter, we did some proofs like this. And anytime that we did a proof like that, we said, okay, if n, for example, was odd, we would say n is equal to 2k plus 1 for some integer k, and we would substitute that back into the expression we want to find the parity of and either prove that it's even or prove that it's odd. So in this case, that would be n odd, but if n was an even number, then obviously we'd be substituting in something even. So it appears that our two cases will likely be that either n is an even integer or n is an odd integer, because substituting in the value will change depending on the parity of n. So let's look at the actual proof. Let's see, the only thing we're assuming is that n is an integer. So proof, suppose n is an integer. And from there, now it's going to break into two different cases. Again, the order in which these cases are approached does not matter. So case 1, let's suppose n is even. Then by definition, n is equal to 2k for some integer k. And so now we can consider n squared plus n, which in this case would be equal to 2k squared plus 2k, which is equal to 4k squared plus 2k. And we are trying to show that n squared plus n, the expression we're looking at right now, is equal to 2 times some integer. So we want to factor out a 2 from that. This is equal to 2 times 2k squared plus k. And so, yes, this is equal to 2 times an integer, so 2k squared plus k, where 2k squared plus k is an integer. And so, by definition, n squared plus n is even. Now let's take a look at our second case, case 2. So if n is not even, then n is odd. So case 2, n is odd, and therefore n is equal to 2k plus 1 for some integer k. Notice at this point that I can use the same variable that I used above. So in case 1 I use the variable k, and in case 2 I can also use the variable k if I wish, or I can switch variables. It doesn't matter. So the cases stand alone as mini proofs. Remember that in general in the body of a proof I cannot make the same variable stand for 2 different things. But when we do case 2, it's like we have started over. We can now use the same variable as we wish because we're on a whole new mini argument or a whole new little self-contained universe. So n is equal to 2k plus 1. Observe that the quantity we want to prove something about, n squared plus n, is then equal to 2k plus 1 squared plus 2k plus 1. And now I need to simplify that. So 2k plus 1 squared, if you do that out on scratch paper, you'll get 4k squared plus 4k plus 1 plus 2k plus 1. And so we can combine terms. We've got 4k squared plus 6k plus 2. And again, we're trying to prove that that's equal to 2 times some integer. Can we factor out a 2? And yes, we can. That's 2 times 2k squared plus 3k plus 1, where 2k squared plus 3k plus 1 is in the integers. So n squared plus n is even. And then we could say something to conclude like, for all integers n squared plus n is even. And that is summarizing both cases that we've examined, and so we've proved it for all integers. We have finished our proof. So when you're doing a proof with cases, I'd like you to always be very clear about the cases. So actually stating this is case 1 and this is case 2 before you begin each mini proof is important. Before the next proof, I'd like to introduce a definition. So 2 integers have the same parity if they are both even or they are both odd. So for example, 3 and 9 have the same parity. They're both odd. And 2 integers have opposite parity if one is even and one is odd. So for example, 0 and negative 7 have opposite parity. 0 is even and negative 7 is odd. So I'd now like you to think about proving the following proposition. If 2 integers have opposite parity, then their product is even. So for example, 2 and 3 have opposite parity, and we can see that their product, 2 times 3 is 6, is even. So there's one example that shows it's true in one case. We want to prove that it is always true. So I'd like you to think about this, and in thinking about it, do you need cases? And if so, what would the cases be? And I'd like you to try out this proof. And so give that a try, and then we will look at it together. Okay, so we want to prove that if two integers have opposite parity, then their product is even. So proof, we want to suppose that two integers have opposite parity. It's useful to give them names. Let's call them x and y. So suppose that x and y have opposite parity. Then by definition, one of those two integers is even and one of those two integers is odd. Okay, so when you approach this above, it's possible that you did this in two cases. So case 1 might be x is even and y is odd, and case 2 might be x is odd and y is even. And if you did that, you probably realized that basically you did the exact same proof twice, that nothing was different aside from the labels of x and y. And so in a situation like this, our goal is to be both clear and concise. So we want to do these proofs in the least space possible while maintaining clarity. So instead of doing too many proofs that are almost exactly the same aside from the label of x and the label of y as even or odd, a really common phrase in mathematics is without loss of generality. Without loss of generality, it's often abbreviated WLOG, WLOG. Without loss of generality, suppose that x is even and y is odd. And again, we can do that because there is no structural or logical difference between x being even and y being odd, and y being even and x being odd. We know that labels given to mathematical objects or numbers do not matter. And again, notice that this contrasts with the previous two proofs. So for example, in the previous proof, we had two cases, n being even or n being odd, and that actually did make a difference in the body of the proof, whether we were looking at n equals 2k or n equals 2k plus 1, change the expansion of n squared plus n, for example. But here we can assume x is even and y is odd, then x is equal to 2k for some k in the integers, and y is equal to 2 times, I need a new variable, 2j plus 1 for some j in the integers. And again, I need a different variable here because I don't want to have created a false relationship between x and y. So for example, if I used y equals 2k plus 1 and x equals 2k, then that would give the additional assumption that y was 1 larger than x. Okay, so I'm trying to prove that the product is even. So consider the product. Consider x times y, which is equal to 2k times 2j plus 1. I'm trying to show this is even, so what I need to do is factor out a 2. That's essentially done for me already. I could leave that 2 on the outside and distribute the k. So this is 2 times 2jk plus k, where 2jk plus k is an integer. And so, by definition, the product of x and y is even. And so I have proven that for a general x and y, any two integers x and y with opposite parity. and my proof is complete.